Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be doing Unit 5, Lesson number 4 on arithmetic series. So for the first 3 lessons, we've been studying and reviewing the ideas of sequences, right? Lists of numbers that you kind of then denote or talk about in terms of where they are in line. What's the first number, the second number, the third number, all the way up to the nth number. Today, we're going to start talking about what are known as series, all right? So to begin, let's find out what a series is. All right, the definition of a series. Let's say we have a sequence whose terms are A1, A2, A3, etc. How many terms are there? Doesn't really matter. But a series is defined by summing, right? Adding up by summing the first n elements. So, we specify that. We say a series with n elements. And remember the summation symbol, right? Just from a previous lesson, right? We always start with the first element, always, 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 and then sum up to some number of elements. So maybe there's 10 elements, maybe there's 20, whatever it is. And all the summation notation is telling us to do is take the first term of the sequence, the second term, the third term, etc., add them all the way up to the nth term. So that's it. A series is simply a summation of the terms of a sequence. Now, why you'd want to do that, we'll eventually find out. But that's all a series is. So it's a pretty simple idea. And let's jump right into it with an arithmetic series example. All right, exercise number 1. The arithmetic sequence is defined recursively using this definition. Which of the following is the value of this? So what I'd like you to do is actually pause the video right now and test yourself to see where you are right now on this problem. All right, well, just to make sure we understand what this means, right? This just means, using the summation notation, right, I'd take the 1, I'd plug it in here, I'd have A1, and then remember I make that go up by 1, and then I plug it in here, and then I'd have A2, and then I'd go move it up, plug it in, A3, etc. In fact, I don't know why I just did ... given that I only have 2 more. In fact, what I want you to be able to do is look at this and go, that just means they want me to add up the first 5 terms of this sequence. Now the problem is we don't have the first 5 terms. We do have the first term. A1 is -2. But then we don't have the other ones. So let's make sure we can interpret this recursive definition, right? And this is definitely an arithmetic sequence, because what we're saying is that every term will be calculated by taking the previous term and simply adding 5, right? That's that common difference, just to add 5. So it's easy, right? A2 will be A1 plus 5, so that'll be -2 plus 5, and that'll be +3. And then A3 will be A2 plus 5. I'm going to kind of skip some of the writing here. 3 plus 5 is 8. I'm going to circle the terms. All right. A4 will be A3 plus 5, which will be 13. And A5 will be A4 plus 5, which will be 18. All right, so we just need to sum them up. Like literally now, this is just -2 plus 3 plus 8 plus 13 plus 18, and that all sums out to be 40. So if you got 40, then you are well on your way to understanding what's going on here, right? Well on your way. So pause the video now, take a look, and answer or and write down anything you need to. All right, I'm going to clear out the text. Okay, so an arithmetic series, that is the topic of today, is simply the sum of the first n terms of an arithmetic sequence. And remember, arithmetic sequences kind of look like this: 3, 5, 7, 9, right? Here's an arithmetic sequence where we're adding, right? We're adding 2 each time. That's that common difference, right? Likewise, we could have something like this where we're adding 5 each time to get to the next term, right? These are all examples of arithmetic sequences. We can obviously add a negative here. We're adding a -6 each time, which of course has then the effect of subtraction. And that's okay to think about it that way too, as long as you recognize that it's an arithmetic series. Right? All of these things are arithmetic series. The question will be now, how can we find the sum of the first n elements without sort of, if you will, doing it the long way? Especially if we had, let's say, 50 elements or something like that. So let's take a look at that with a beginning exercise. Okay, exercise 2. Consider the arithmetic sequence defined by a1 equals 3, that's the first one, and then each term is defined as the previous term plus 2. So, right, we go up by 2 each time, plus 2, etc. All right? The series, based on the first 8 terms, so that'd be like S sub 8, all right, of the sequence is shown. Terms have been paired off as shown. All right, now why we're pairing them off, we'll take a look at in a bit. Let me just get rid of this. All right. Let's take a look. Letter A, what does each of the paired off sums equal? Yeah, it's pretty easy to see, right? 3 plus 17 is 20. 5 plus 15 is 20. 7 plus 13 is 20. 9 plus 11 is 20. Each one is 20. Now, more importantly, letter B, why does it make sense that this sum is constant? That this sum is constant? Think about that for a minute. All right. Well, it's maybe a little bit hard to even verbalize this, but I would probably say something like this. As you move right in the sequence, you add 2. But as you move left, you subtract 2. And that leaving the sum a constant, right? So the fact that the 3 plus the 17 is 20 is just what it is. But then when we go to the next term, we add 2 here, but we subtract 2 here. And therefore the 5 plus the 15 continues to be 20. And then we add 2 here, and we subtract 2 here, and the 7 and the 13 continues to be 20. How many pairs are there? Well, that's simple enough. There's 4 of them. 1, 2, 3, 4. Most importantly, though, why are there 4 pairs? So pause for a minute. I mean, it's easy enough to go, yeah, there's 4 pairs. But why are there 4 pairs? Think about this. Do you have it? Right, there's 4 pairs simply because there are 8 elements, right? The number of elements divided by 2, right? That gives me the number of pairs. Using your answers from A and C, find the value of the sum using a multiplicative process. So what would be the value of that sum? Hopefully you figured out 80, right? There's 4 pairs. They're worth 20 each, so there's a sum of 80. Letter E. Generalize this now and create a formula for an arithmetic series based only on its first term, its last term, and the number of terms. So think about this. We got A1 plus A2 plus A3 plus ... all the way up to AN minus 1, AN. And I want to add these all together. So I want you to think a little bit about what that formula would be. Pause the video now and try to come up with a general formula for adding the terms of an arithmetic series, or adding the terms of a sequence to get a series. All right, well, it's this simple, right? Generalizing this process, we can always pair these things off, and they will always have a sum of A1 plus AN, right? That's this thing. That's that 20. The question is, how many pairs will there be? Well, we can always take the number of elements and divide by 2 to give me the number of pairs. And then this will give me the sum of that series. And it's really kind of cool because what we're doing is we're using the structure of an arithmetic sequence and the fact that the terms of an arithmetic sequence will pair off in these constant sums. We're using that to then be able to generate the sum of as many elements as we want, as long as we know the first one, the last one, and how many there are. The first one, the last one, and how many there are. And I'm going to emphasize that for the rest of this lesson. Okay? Pause the video now and write down anything you need to. All right, let's clear out the text. The sum of an arithmetic series. A1, A2, A3, AN, and there's that sum. So if you couldn't read it very well in my handwriting, go for it. And again, I just really want to emphasize something. We need to know 3 things. The first term, the last term, and how many terms. Isn't that cool? All right. So let's do it. Let's do a problem on this. Which of the following is the sum of the first 100 natural numbers? Now, all by itself, this piece of terminology is not really important for you to know. But the natural numbers are 1, 2, 3, 4. The way that I always explain them to my students is that they're the numbers that are most natural to a child, right? When a child first learns about numbers, they don't learn about 0. They start with the number 1, right? And then 2 and 3 and 4. You don't start talking about halves and zeros and certainly not negatives and fractions for a long time. Anyway, this is definitely an arithmetic sequence, right? Because you have 1, 2, 3, 4, etc. The arithmetic series would be 1 plus 2 plus 3 plus 4, all the way up to 98, 99, and 100. So we've got this formula, right, that says, well, as long as I know the first term, the last term, and the number of terms, I can calculate this. So this is awesome, right? My first term is 1. My last term is 100. And again, keep in mind that what that sum is, right, is it's simply what each one of these pairs would add up to. Right? Each one of these is going to add up to 101. How many pairs are there? Well, there's 100 total numbers, and so we must end up with 50 pairs. Each one of them having a sum of 101, and when I work all that out, it comes out to 5,050. All right. Now this was a pretty easy problem because it was fairly straightforward about what was the first element, what was the last element, and how many of them were there. In some problems that we're going to look at in a moment, we're going to have to do a little more problem solving to figure out those 3 pieces of the formula before we can even evaluate it. So pause the video now, write down anything you need to, and then we're going to do some more challenging problems. All right, let's do it. All right, find the sum of each arithmetic series described below. All right, well, letter A is not too bad. Okay, why don't you go ahead and try letter A. Pause the video now. All right, let's go through it. So again, to do the sum of any arithmetic series, right, that sum, S sub n equals n divided by 2 times a1 plus an. Look at how small I can write when I really want to. Think about what we need. We need the number of terms. Do we have it? Sure, we have 16 terms. We need to know the first term. Do we have that? Sure, it's negative 10. We need to know the last term. Do we have that? Yeah, it's 50. So this one should be easy. I'm going to even use the subscript notation. S sub 16 is equal to the number of terms divided by 2. That gives me how many pairs I have. And each pair is going to have a sum of negative 10 plus 50. I keep wanting to emphasize the structure of this formula, because a lot of students will look at it and just memorize it. I want you to look at it and understand it. Okay? Now again, that was pretty easy. But take a look at letter B, pause the video, and think about that formula. Think about the formula. I'm going to circle it in red so that we have it just up front. Think about this formula and what you are going to need to work it out. So pause the video now and look at letter B. All right, well, let's go through it. It says the first term is -8, so we have A1. That's good. The common difference, D, is 6. Well, that's nice. And there are 20 terms. That's N. What we don't know is we don't know A sub n. We don't know that last term. All right, and we need it. So what we have to dig into now, actually, I don't want to erase that, is we have to use this formula. A sub n is equal to A sub 1 plus n minus 1 times d. You remember this? So this is a formula that we had just a couple lessons ago when we looked at arithmetic and geometric sequences. And this allows us to produce the nth term. I guess it would be the 20th term, right? That's going to be our last term by taking our first term, -8, and adding 1 less the number of common differences. So remember, to get to the 20th term, we add the 6 9 times. And that gives us our last term at 106. And that's all we needed, right? We need our first term, we need the number of terms, and we need our last term. And now we can say that the 20th sum is the number of terms divided by 2, 10 pairs, times the first term, which is -8, plus the last term, which is 106. And again, this is just kind of nailing it all out, and eventually we'll get a sum of 980. All right? Now, it is really critical when you do arithmetic series work, you oftentimes need the arithmetic sequence formula, right? So you want to keep that one handy. Okay, let's take a look at letter C. The last term, A12, is -29, and the common difference, D, is -3. So again, pause the video now and see if you can figure out what the sum of this arithmetic series is going to be. All right, let's work on it. Well, again, we have only 2 of the 3 parts of the puzzle. We definitely have how many values there are. There's 12. We definitely have the last one. We have A sub n. It's -29. What we don't have is A1. We don't have the first term. Again, we're going to use my arithmetic sequence formula to figure out what that first term is. The weird thing is now we're looking for this, not this one. This is the one we have. We've got the -29. We don't know what A sub 1 is. We do know that we have 12 terms, so n minus 1 would be 11. And we do know what the common difference is. It's -3. So I'll get -29 equals A1 minus 33. And if I add 33 to both sides, so I want to save myself a little bit of room, I'm going to find that my first term was +4. All right? But now we have everything we need, right? We have our first term, we have our last term, we have the number of terms. So the 12th sum is going to be the number of pairs, right? 6 of them, times my first term, plus my last term, that common sum, and we end up with a total sum of -150. All right. Well, take a look at the last one. This also presents us with a conundrum. Conundrum. Anyway, pause the video and think about it. All right, let's take a look. Well, this one's awesome. It seems like I have everything. I've got my first term. I've got my last term. But I don't know the number of terms. Ugh. And each time each time we keep going back to this formula. Because this formula really is what relates the first term, the last term, the common difference, and the number of terms. This one's going to be a little more challenging, okay? But I can use it still to find n, right? Because I know the last term's 77. I know the first term's 5. I don't know the number of terms, but I do know the common difference is 3, right? So the beautiful thing is this equation now only has the number of terms in it, and I can solve it, right? 77 equals 5 plus maybe 3n minus 3. Let's say I distribute the 3. So 77 equals 3n plus 2. Got to save myself some room. 3n is going to be 75, and n is going to be 25. We have 25 terms. Now let's take a look at the sum. This is kind of funky, actually, 25. Because even though we have 25 terms, therefore we have an odd number of terms, this still works just fine. We have our first term, we have our last term, right? And we just crank through that calculation, and we find that we have a sum of 1,025. All right? So that's it. There's a lot on this page, a lot we did. So I want you to pause the video now and take as much time as you need to write things down and to think about what we did. All right, I'm going to clear out the text. All right, one final problem, nice applied problem. Kirk has set up a college savings account for his son, Maxwell. If Kirk deposits $100 per month, what is that? If Kirk deposits $100 per month in an account, increasing the amount he deposits by $10 per month each month, then how much will the account be? Well, how much will be in the account after 10 years? So again, let's make sure that we understand this. Kirk deposits $100 per month in an account, increasing the amount he deposits by $10 each month. So sort of the first month, if you will, Kirk deposits 100, the second month 110, the third month 120, etc. And then I'm going to add these all up. How much do we have? All right. See if you can figure this out, given everything that we have. Clearly, this is an arithmetic series because it's based on an arithmetic sequence that goes up by 10 each time. But think about this and see if you can figure out how much we have in that account at the end of 10 years. All right. Well, let's write down the formula one more time. S sub n equals n divided by 2 times a1 plus an. Well, what do we know? Do we know the number of terms? Well, no, but I think I can figure it out, right? We've got 10 years, 12 months per year, 120 months, so 120 terms. So I've got that. Do I know the first term? Yeah, it's 100. Do I know the last term? No, I don't. But I can go back to my handy-dandy friend a1 equals n minus 1 times d, right? And I can say that a sub 120 will be 100 plus, well, 119 of those raises by the common difference 10, right? That common difference is 10. So I know that my A120 is 1290. Wow. So in the last month, I'm depositing 1,290 into my son's account. Max is my son. So let's add them all up. S120 is going to be 120 terms divided by 2. That gives me how many pairs I have. The first term, a measly $100 that I'm depositing, plus my last term, 1,290, right? And all of that will sum out to a whopping $83,400. That's it. All right, so pause the video, Write down anything you need to. Okay, I'm going to clear out the text and then we'll wrap up this lesson. I'm going to try to clear out the text. There we go. All right, so today we were introduced to a series for the first time. And a series is a very simple idea. We are simply adding up the first n terms of a sequence, starting with the first term, going up to whatever, the 5th term, the 10th term, the 22nd term. Okay, it all depends on what the problem is asking for. Then we specifically segued into arithmetic series and tried to generalize a formula for finding those based on the structure of an arithmetic series, i.e., if we look at this series, the sum of an arithmetic sequence, every time we go up a common difference on one end, we go down by a common difference on the other end, right? And therefore, when we sum them all up, we get these pairs of sums that are always the same. And we can exploit that structure to come up with that formula that we showed you. All right, enough for that for now. I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.